Welcome to Power Machines N6. This is the first of a series of 2 videos on cycles. For today, we're going to look at the Otto and the diesel cycle. But first, let me begin by reminding you of some of the things you learned in Power Machines N5. The first of which is the characteristic equation, which is written like this: PV is equal to MRT. And what that means is that the product of the pressure and the volume at a given state is equal to the mass multiplied by the gas constant multiplied by the temperature of that substance at that state. So if, for instance, you are at state 1, therefore the characteristic equation will be P1 V1 is equal to MR T1. And I remind you that T1 is a temperature in Kelvin and not in Celsius degrees. Do not make that mistake. And so the characteristic equation can be written like this, but another way of writing it is to say that the product of the pressure and the volume divided by the temperature before a certain process is equal to the product of the pressure and the volume divided by the temperature after that process has taken place. So if, for instance, between states 1 and state 2, you have maybe combustion that takes place. Therefore, the product of the pressure and the volume at state 1 divided by the temperature at state 1 must be equal to the pressure at state 2 after combustion has taken place multiplied by the volume at state 2 and divided by temperature at state 2. So that's the characteristic equation. I'm sure some of you watching this video remember that. The other thing I need to remind you of is the polytropic equations. Now, when a process is polytropic, it obeys the law P multiplied by V raised to the power of N is equal to C. And here I need to draw your attention to something. It's not the product PV that is raised to the power of N, but rather it's P multiplied by V, and it's only V that is being raised to the power of N, and that must be equal to C. N that you see here is called the polytropic index. So if you have a certain process, could be compression or maybe an expansion process, if you are told that the expansion is polytropic, it means that it obeys this law. And the N, again, I repeat, is called the polytropic index. Now, this equation can be written like this. So the product of the pressure multiplied by the volume raised to the power of N before a certain process is equal to the product of the pressure and the volume raised to the power of N after that process has taken place. So if, for instance, you have a compression process between state 1 and 2, so the substance was at state 1 and then compression takes place. Now you see the substance being at state 2, okay? Then the polytropic equation can be written like this, okay? So P1 V1 to the power of N will be equal to P2 V2 to the power of N. But for you to be able to use this equation, you have to be told in the question that the process was polytropic between state 1 and state 2. Sometimes they may not say that it's polytropic, but they will just say take the polytropic index as being maybe 1.29 or something like that. Immediately when they give that away, you know that this process between 1 and 2 was polytropic, and therefore you can use the polytropic equations. But do not use polytropic equations when you are not told that the process is polytropic. All right? And other polytropic equations can also be created using mathematical principles and the characteristic equation, and those ones will relate the temperature to the pressure and the temperature to the volume, as you see here. So the 3 polytropic equations that we have on the screen are this one that relates the pressure to the volume, that relates the pressures, I should say, because it's more than one pressure, to the volumes, because it's more than one volume. And then you have the other polytropic equations here that relate the temperatures to the pressures and the other one relates the temperatures to the volumes. Okay, so these are the polytropic equations. And when you are told that a process is polytropic, it's important that I also remind you of the equation of the work done for a polytropic process. Okay, so if you have a polytropic process between state 1 and 2, the work done is given by the equation that you see here, P1 V1 minus P2 V2 divided by n minus 1. And remember, from the characteristic equation, PV is equal to MRT. So P1 V1 will be equal to MRT1, and P2 V2 will be equal to MRT2. And so you can rewrite this equation for the work done for a polytropic process and have it look like this. Okay, really important to remember these. Okay, and so next, let us look at the piston and cylinder. The reason I wanna explain a little bit here is because I know that some of you listening to me right now are not from the mechanical engineering school, so maybe the piston and the cylinder are not very familiar to you. So I am gonna spend some time explaining what a piston and cylinder arrangement is. Okay, so what you have on the screen is a piston and a cylinder, and the piston is that thing that you see here. Okay, that is what we call the piston, and the piston is usually connected to a piston rod, and the piston rod is connected to the crankshaft. And the cylinder is the casing in which the piston is moving. Okay, the piston moves inside of the cylinder. Okay, and what you see here are not really important. They are called piston rings. Okay, they're not really important, but what I want you to focus on is the piston and the cylinder. And so as the crankshaft is rotating, the piston is moving up and down inside of the cylinder. Okay, and on top of the cylinder you also have a few components that I need to show you. This one here is the inlet valve, and then on the other side you have the outlet valve, and on top of the cylinder you have the spark plug. Okay, so for those of you who've looked at the engine of a car, you can see on top of it somewhere you will be able to find where the spark plugs are, and the number of spark plugs that you see on the engine will also tell you how many cylinders that engine has, because you have one spark plug per cylinder. Okay, and so the way this works, okay, is that initially you will have the piston moving down. When the piston is moving down, the inlet valve will be open, but the outlet valve will be closed. And so what will happen as the piston is moving down, it will act a bit like a syringe, and it will suck in substance here, which is a mixture of air and fuel and gases, and that will be sucked in the cylinder as the piston is moving down. And as soon as the piston reaches the lowest position that it can reach, which is called the bottom dead center, okay, BDC in short, bottom dead center, when the piston reaches the lowest position, the inlet valve is going to close. So now both the inlet valve and the outlet valve are closed, and then the piston will again begin to move up. But now, because the mixture that is inside the cylinder has nowhere to go as the piston is moving up, because both valves are closed, okay, so that mixture will begin to be compressed. And as compression is taking place, the temperature of the mixture is going to increase, and the pressure is also going to increase. And eventually the piston will reach a position that is very close to its topmost position, which is called the top dead center, TDC, okay? And when it reaches that position, immediately the spark will ignite, the spark plug will release a spark, okay? That is why it's called the spark plug, because it releases a spark, okay? And because already the mixture inside of the cylinder was already at a high temperature and a high pressure, that little spark that the spark plug is going to release is going to cause a sort of explosion inside of the cylinder. And when that explosion will take place, that will cause the piston to move down, okay? And when the piston moves down, Again, it will start moving up, but this time the outlet valve will be open. And so the mixture that has just gone through combustion is then going to be exhausted through the outlet valve. And that is what you see coming out of the exhaust pipe of your car. Okay? And so what is really important that you need to understand also here is that the distance through which the piston moves from its topmost position to the bottom position is called the stroke length. And so the volume that the piston displaces when it moves through its stroke length is called the stroke volume. Very important, okay? But if you look at this picture carefully, you will see that the piston does not go all the way up to the top of the cylinder. The reason for that is because you do not want to crush the components of the cylinder, such as the valves and the spark plug, okay? So the piston never goes all the way to the top, okay? But there is always a certain volume on top here through which the piston does not move, okay? It doesn't move in this volume. And that volume is what is referred to as the clearance volume. Okay, and so the maximum volume that you can have in the cylinder at any given time is when the piston is at the bottom dead center. When the piston is at the bottom dead center, then you have a great volume inside of the cylinder. But when the cylinder is moving, okay, maybe at the position where you see here, okay, where it is here, the volume inside of the cylinder is only that, okay? So that volume is going to be equal, of course, to the clearance volume, which is always there, plus that volume that you see here, okay? And so that will give you the volume inside of the cylinder, okay? Again, I repeat, the maximum volume that can be found in the cylinder is when the piston is at the bottom dead center, because then you have all of the stroke volume plus also the clearance volume. But all of that is going to make sense very, very soon. Okay, now let us look at the first cycle I wanted us to look at. And that is the Otto cycle. Now, the Otto cycle is also referred to as the constant volume cycle. And the reason for that is because when you look at the diagram of the Otto cycle, you can see that state 1 and state 4 have the same volume. And state 2 and state 3 also have the same volume, okay? So that is why the Otto cycle is called the constant volume cycle. And also on the pressure axis, we can look at the pressures of state 1, P1, the pressure of state 2, P2, the pressure of state 3, P3, and finally the pressure at state 4, which is P4, okay? Really, really important. So now what you're seeing here is what is referred to as the PV diagram of the Otto cycle. Okay, all of the cycles have their own PV diagram, okay, but if you want to solve a question on cycles, it's going to be really important for you to know how the PV diagram of that cycle looks like. So when you're dealing with the Otto cycle, this is what the PV diagram of the Otto cycle looks like. It always looks like that. So when you get a question on the Otto cycle, you can already begin by drawing the PV diagram of that cycle. That will give you a good idea and a good pedestal on which to stand in order for you to solve the problem. So now, between state 1 and state 2, okay, to move from state 1 here to state 2, okay, the process that is taking place here is a compression process, okay? The process between state 1 and state 2 is a compression process. The process between state 2 and state 3 is a combustion process. The process between state 3 and state 4, okay, is an expansion process, as you can see, because the volume is increasing. And the process between state 4 and state 1 is called the exhaust. Okay, so initially the mixture will be at state 1, and then it's going to be compressed to state 2. And as you can see, the volume is decreased. We move from V1 to V2. And then when it is at state 2, combustion takes place until we reach state 3, okay? And at state 3, expansion takes place and the volume is increased again to state 4. And then from state 4 to state 1, this process is called the exhaust, okay, the exhaust phase. Really, really important. So it's really important for you to know the Otto cycle PV diagram, okay? It looks like that.